In July 1970, Rudolf Baer and McWright from Boeing Scientific Research Laboratories have published the original bitwise paper. They published it in the Mathematical and Information Sciences report. They never said actually what the B in the bitwise stand for. It could well be that the B in bitwise be Boeing trees, though balanced trees is also a good reminder of what they actually are. When studying bitwise, before we get to the actual algorithm, wouldn't it be nice if we understand the exact motivation of the people who actually published the original paper in 1970? The original people who thought of this idea. They explained their motivation in the paper. But first, just remember that we are talking here about 1970. This was before most of us were born. Computers were very slow, really slow. In the paper, they said that they are working on the organization and maintenance of index for dynamic random access files. Let's dissect it. We know what an index is. This is a thing that allows us to locate items fast in our data without needing us to scan the whole data structure, right? So they want to understand and also to suggest a better way to organize and maintain such an index. So one of the key issues that bitwise tries to solve is not only search but also sequential access into items. Once you have a page, once you load a page from disk into memory or also inside the disk, then it's sequentially sorted, each page, each key, each node that holds keys. So if I'm a node and in my node I hold 10 keys, then I can sequentially get the keys from the smaller to the larger in that page. And this is very helpful because if we have a slow disk, especially if we have a slow disk in the 1970, then we don't want to move the head of the disk all around the disk. We want to get the page and we want to get the similar object, the sequential objects, right after another. We want them to be physically located one next to another on the disk. They use a random access backup store. This is what they talk about. So even on the 70s, they are talking about a backup store. I'm emphasizing this because they are talking about this backup store as a very slow device, like a disk or a DRAM. So this separates the bit trees from other balanced trees. In the bit trees, not only we want our index to be balanced, but we also want our index to be sequentially organized so that it's optimized for slow disks, or as they say in the paper, slow backup stores. Rudolf Baer and Edward McWright, they want to achieve from this index retrieval, insertion and deletion of keys, which should all be running in logarithmic time relative to the size of the index. In the actual experiment that they did and they describe in the paper, they had up to 100k indices and they maintained it with their bittree method, and they presented that they have achieved up to 4 transactions per second. They used the computer IBM 360/44 with a 2311 disk. So in this paper, they talk about how to dynamically maintain such an index, because such an index can receive new keys, you delete from it keys, and you want to keep its structure in a way where it's efficient. It's always keeping the logarithmic time. And you also want the sequentiality because you are storing on, as they described, a backup store, a disk. So they use random access files, which means that the time to get any item from the disk is equally. However, once you get a block from the disk, then you can read all the items very fast because you are already in that block. And the key deletions and when you insert items and when you get items from the disk, then they call it paging. Why paging? Because they hold all the page in memory, because it was originally presented as a data structure for dynamically maintaining indexes where on disk. This is why B-trees is very useful for databases, because databases store a lot of data. And you want exactly these qualities out of indexes of databases. You want to be able to store a huge amount of data, so you want to be efficient. If you want to be efficient, you don't want to waste time on the disk. If you don't want to waste time on disk, you want blocks that have sequential items, that you can load a block and you won't use just a specific item from the block, but the whole block, or as much as you can from this block. And this is why if you're ever asked what is the most, how do databases do indexes, then in most cases it's simply B-trees. So let's think about what we want of such a data structure, and this would enable us to build this B-tree even before knowing what this B-tree is all about. At least except for the algorithm of the insertion and the deletion, etc. So what is mainly the core of this data structure, this B-tree? We want to be able to search in a logarithmic time. We need therefore a kind of a search tree. But in standard search trees, if you insert all items in a linearly increasing way, then you might end up with a simple line tree, which won't be efficient. It would be orphan. So we need to rebalance this tree. We must, otherwise, if we don't rebalance this tree, then we won't get a logarithmic insertion and deletion and search logarithmic time. In addition, as our memory is limited, then we want to store part of this tree in memory, but also all the rest of the B-tree on disk. Once we store some part of the tree in memory, let's call it a page. Once we stored a certain part of the B-tree in disk, let's call it a page. So the act of moving in between the memory and the disk is paging out and paging in the B-tree. Once we have such a page, we could just, it's a node in the tree, we could just linearly go through the items inside the node. Now, why would we want to have more than one item in a single page? Why not only two? Because we store it on disk. Once you store stuff on disk, it becomes slow, much slower than memory. The fact that the disk is slower than memory means that we want to store them sequentially, such that when we load a block, we didn't waste the whole block. So that at least moving from one item to another on the disk inside the block would be fast, because we only need to take the block and read the items and not move the head from one place on the disk into another place on the disk. So now that we understand that the tree needs to be rebalanced, and not only needs to be rebalanced, but we want to store cohesive blocks. So meaning each node of the tree would have multiple keys and not just one key, so we don't waste our blocks and we are efficient with the disk. Within each such page, P, the keys are sequential in increasing order, x1, x2, x3, where x2 is larger than x1 and x3 is larger than x2. Except for the root node, each such page contains, each B-tree has what's called a degree. A degree is the max amount of children that a node can have. It can have degree minus 1 keys and degree children. And by the way, in the paper, they call the children the sons. I guess they lived in a non-politically correct era. And now to the actual algorithms for the insertions and the deletions. We want to avoid the whole line in the tree. We want it to be balanced. An unbalanced would be orphan, while a balanced tree, the search and the deletion, everything would be of logorphan. If we want to insert a new node into the tree, then as always in search trees, we start from the root, we find the correct place, we go from the root of the tree to the bottom, and we move to the left if our key is less than the keys on the root, or to the right if our key is more than the number of keys. However, if the key fits into the root and we have enough keys to insert according to the degree of the tree, then we can just insert this key in the root. So if you have a degree of 30, then you can add more and more keys to the root until you reach the limit. And only then will you need to create new nodes. because each bit tree has what's called a degree. The degree is the max amount of children that a node can have, and each node could have degree minus 1 keys. When you insert a new number into the tree, then you find its correct place. If you don't have enough room for this new key, then you split the node that you're having, and you promote the median into the parent node. If you try to promote a new key to the parent node, and you don't have enough space in the parent node, then you split also the parent node. But then, if you are splitting the parent node, that you might need to increase the height of the tree by 1, and this is how the tree is growing. So you start from the root, you find the correct place for the new node that you want to add. If there is no space, you split the node, and you move up, and you split the nodes, and if you can't split them, then you simply increase the height of the root, the height of the tree. So let's start with an empty tree. We insert 5. Let's say it has a degree of 3, which means we can have up to 2 keys in each node and up to 3 children for each node. The degree is the number of children, up to how many children, and up to k minus 1 keys in each node. So we start with an empty tree, we insert 5. So we now have a single root node with 5, all is fine. Now we insert 10. We look at the root node, it still has space, the degree is 3, so we can add up to 2 keys in the root node. So we just add 10 to the root node, everything is fine. We have both 5 and 10 keys on the root node. However, as the degree is 3, then the next time we would need to insert a new node, we would need to split the root. So now has come the time to split the root because we insert 15. So we already have 2 keys in the root node. We cannot insert 15 because we can only have k minus 1 keys, which is 2. So we insert 15 and we split the root node. So we had 5 and 10. The median is 10. So now the root is 10 and we have a left child of 5 and the right child of 15. Now let's add 7. So we start from the root, we look, we have 10 on the root. So we move to the left because 7 is less than 10. So we have 7 as a brother child, as a brother key to 5 that we already have. So we have 10 as the root node. On the left child, we have 5 and 7. And on the right child, we have 15. Now let's add 4. 4 is less than 10, move to the left child. 4 is less than 5 and 7. However, we can't add it to the left child because we already have 2 keys. We have a degree of 3, so this means we have up to 2 keys, k minus 1 keys. So we split the node. 5 is the median. So we're going to have 4 to the left, 5 as the median, and 7 to the right. So now our root node has 2 keys, 5 and 10, and 4 and 7 are on the left subchild. So to sum up the bit trees is a self-balancing tree data structure that maintains search and sequential access and insertion and deletions in logarithmic time. You can insert, search, and delete in logarithmic time while you have a certain amount of keys that you can have in each node, and this allows you to treat the nodes as blocks that you store on disk, and once you have a block you can reach all the keys sequentially. The way to insert new items into the tree is to find the place, because it's a search tree, so you find the place. However, when you found the node that you want to add the key into and this node is full, then you split it. But if you have reached the limit, once you have split the nodes of the number of children, then you have to split also the parent, and then you have to split also the parent of the parent, because you have reached the max number of children, and then you, like this, increase the height of the tree. When we insert a new node, we search the tree and we find the leaf node where the new element should be added. We add the element into a new node. If the node that we find that we need to insert the key is fewer than the max allowed of keys, then it has a room and we just insert the node. However, if it's full, then we split the node into 2. We have a single median, which is chosen among the left elements and the new element together. Values which are less than the median are put on the left node, and values which are greater than the median are put on the right node. And the median is acting as a separation of values. The separation value is then inserted in the node's parent, but this can cause also the parent to split, and so on. If the node is the root and we need to split it, then we need to create a new root above this node. This forces us to increase the height of the tree. So this was a brief summary of bitwiz. We scanned the origins, we scanned the limitations, and how to insert a new node. And once we insert a new node, whether we want to increase the height of the tree or not.